Every day of delay of an NVIDIA Blackwell costs the company something like $225 million. Chips are the fuel for AI. The industry needs this immediately. This is one of the big bottlenecks.
Anna Goldie, founder and CEO of Ricursive Intelligence, co-lead of AlphaChip at Google, the deep reinforcement learning system for chip design published in Nature, senior staff research scientist at Google DeepMind working on Gemini, early member of technical staff at Anthropic when the company had less than 30 people, holds a Bachelor and Master of Engineering from MIT and a PhD in computer science from Stanford, named to MIT Technology Review's 35 Innovators Under 35, and the company she founded 2 days after leaving Google. Every major semiconductor company in the world has already come knocking.
That day I got an email from this Sequoia general partner who actually later became our first board member. She wrote a 30-page report about just me and Azalia, and then she wrote another long memo about the company as well.
The semiconductor industry was already begging for this. She just had to build it.
Phase 1 of the company is we want to tackle the long poles in chip design and make them much faster. Phase 2 of the company would be, let's become a chip design platform. Say the next Claude model and design an architecture customized to that model. Suddenly, any company that had a workload that they serve at sufficient scale to benefit from custom silicon could have their own chips.
But the real ambition goes deeper than speed. It's about something AI researchers call the scaling law, and what happens when you can bend it.
If you can design chips that are better suited to the workloads, to the ML models, you can effectively bend the scaling laws.
Yeah.
So it's never the chip in isolation, it's never the algorithm or the model in isolation. It's also how you map the algorithm onto this chip. It's all holistic.
Which brings us to phase 3, the part she named the whole company after.
If we have this capability to rapidly design highly performant chips, why not build our own chips? Why not train our own models, co-evolve them, and then serve intelligence at a price or a capability that would be impossible to match? That's the recursive self-improvement part.
I'm Jing. As a founder myself, I learned something about this journey. The best way to build a startup is not to read a manual, but to learn from your fellow founders' stories. Before we dive in, I have a small favor to ask from you. If you find value in conversations in this channel, please hit subscribe button and turn on notifications. It helps us keep the mission going. And this will be the only favor I will ever ask of you. Anna, really great to catch up with you again.
Yeah, it's really great to see you too.
It's not that long time. I feel like the world has changed. There's a lot of things happening. And super excited to have you come back. And a lot of our audiences actually request part 2 from Anna. So finally we're making it today. Last time we talked about your careers, and today actually I want to learn about, you graduated in the PhD program in June 2025, is that?
That's right, yeah.
Yeah. And how was the experience of doing both a PhD program while also work at the frontier research?
I would say it was very challenging because I think that being part of 2 different organizations at the same time is hard on its own. You have 2 affiliations, but also just each of these jobs is more than a full-time job.
Yeah,
so a PhD program is not something you do 40 hours.
Right.
You work all the time. And then same for working at Google Brain or Anthropic as an early employee. So, that maybe I was working 70, 80 hours a week at Anthropic, and then so I was, at least for me, I thought it was pretty challenging.
I could imagine it's very demanding. What are the special thoughts that you use to handle all those demanding work?
I think I was very ruthless about saying no to anything outside of these 2 areas, which was already a lot.
Yeah.
I remember very aggressively tracking my time, tracking the things that I was going to take on. And kind of having these very long-term objectives to keep myself motivated, because it was 6 years of this.
In terms of long-term objective, I know that you have a super long-term horizons of career planning. All the careers that you had is focusing on making the AI to be able to design chips faster. And is that also the research that you are focused on?
Initially, I was co-leading this team with Azalia, on AlphaChip and other AI for chip design research at Google. And my work at Stanford was completely disjoint. So I was working with Professor Chris Manning, who is one of the foremost experts in natural language processing. And he did not have any interest in chip design. So there was no overlap at all between my research at Stanford and my work at Google. So that was pretty challenging. To me, I saw this overlap, or I saw this sort of underlying shared structure between these tasks, basically these long-term, multi-step planning problems. So my dissertation actually at Stanford was about, ironically, as you were saying, having a longer-term strategic thinking. It was multi-step reasoning in both natural language processing and chip design. So that's how I could bring those works together. And the other spiritual relationship is the reason originally that I was interested in doing AI for chip design is because I thought that was the best way to advance the state of AI or natural language processing. And so I truly meant that. And then in my dissertation, I was saying chapter 1 was AlphaChip. And all these follow-up works. And then chapter 2 was I said, or part 2 was all this natural language processing, or RL for large language models research. And I said, all of the experiments in part 2 of my dissertation were run on TPUs designed in part by AlphaChip, the part 1.
Yeah, exactly. You actually mentioned about a very great point, which is that in the AI research, there's different subdomains. There's RL for chip design, there's language, there's vision. But if you take a step back and think about the broad picture, they all follow some principles.
Exactly.
Like you mentioned, the multi-step reasoning, that is actually the core reason for that. And then everything's on top of it, the chip design or language or vision, that's applications.
Exactly. And there are certain techniques you can use to, say, reduce the instability of training or be able to handle attribution over long time horizons. And those apply to language tasks or chip design tasks.
You also started to apply those research into industry, and you decided to start your own company.
Yes.
Yeah, tell us more about your company.
So I started this company called Recursive Intelligence. We're doing AI for chip design and chip design for AI, so hence the recursive part. I was very attached to recursive. It felt like in one word, it kind of encapsulates the whole idea of the company. Right. That because it's not just AI for chip design, but it's actually the full loop. I think I mentioned actually in the last episode, I've always been drawn to problems that have this recursive self-improving structure. If you solve this problem, it actually feeds the solution of that feeds back in. And so I think that's super powerful. And I wanted to capture that property in the name of the company so that people would see where we're headed here. What is the final form of this company?
What is your vision of your company for how you want the state of chip design to look like?
Okay, that's a good question.
Yeah.
Maybe I could describe the 3 phases that we see the company.
Yes.
Yeah. So we're currently in phase 1. Yeah. So phase 1 of the companies, we want to tackle the long poles in chip design and basically accelerate chip design, make it, instead of taking 2 or 3 years to produce a new chip, we want it to take much less time. And the way to do that is to take the long poles, physical design and design verification, and make them much faster. And in this phase, we can help existing chip makers, companies like NVIDIA or AMD or Samsung, to design their chips faster. And there's a ton of value in that. We've seen estimates every day of delay of an NVIDIA Blackwell costs the company something like $225 million. So phase 1 is very important. It's very interesting, very challenging. Phase 2 of the company would be, if we can accelerate these long poles, let's become a chip design platform. So let's take as input, say a model, let's say the next Claude model, and design an architecture customized to that model. And, we've done research previously at Google that suggests that you can get multiplier, order of magnitude or more improvements in performance per total cost of ownership by customizing the architecture to the model and then do the whole design process all the way to GDS2 clean. So that's an interesting, suddenly any company that had a workload that they serve at sufficient scale to benefit from custom silicon could have their own chips, even if they don't have teams of hundreds or thousands of human experts on staff.
Yeah.
So that's interesting. But phase 3 is the recursive part. So phase 3 would be, if we have this capability to rapidly design highly performant chips, why not build our own chips? Why not train our own models, co-evolve them, and then serve intelligence at a price or a capability that would be impossible to match? So that's the recursive self-improvement part.
So in this phase 3, what I hear is like phase 1, you will help to make the existing design process more efficient.
Yeah, exactly. Help existing chip makers design their chips faster and better. And we're very excited about that. And that's the foundation for the phase 2 and then phase 3.
Yeah, yeah. And the second one is basically you will be very good at designing chips.
Yeah,
yourself.
exactly.
And this third one, the AI is starting to design chips themselves.
Phase 2 is like, let's go from fabless to designless.
Yeah.
Let's make it such that any company can design custom silicon and benefit from it. And then phase 3 is like, let's vertically integrate.
That's a very fantastic vision. I assume that like spans over how long? What's the timeline for that?
I mean, we'll see. I feel like we've made faster progress than I ever imagined since starting the company. So the timelines that I find myself predicting keep like tightening. But yeah, I think the reason I wanted to name the company Recursive, and Azalia also wanted that, was because we wanted to keep this North Star clear of phase 3.
That's great. Like the vision and the name of company combined together.
And then the name itself, I guess people often ask, like, why is it with an I? So the name, there's a couple of reasons. One is that the name itself is recursive. So the initials are the same as the first 2 letters. Yeah. Recursive Intelligence. Yeah. And then also, like, it's got better SEO. We can get the domain name. And, and also, like, it's a tradition, right? Google is a, alternate spelling of Google. It's a time-worn tradition to have an unusual spelling for your name. So we're following that too.
That's cool. I want to dive a little bit into the phase 1 because you briefly mentioned about currently the chip design, the very lengthy process the last like a couple of years. Yeah. Can you walk through a little bit of like what exactly the current chip design processes and what is the part that you are trying to optimize? So
the first phase would be basically the macro architecture. So designing like what are the dimensions of, say, the systolic array in a TPU, what's the memory hierarchy, those kind of decisions. And those decisions are very consequential. That's where you can get like a 10x improvement in performance per total cost of ownership or maybe more. But they're not done in a particularly data-driven way right now. So how it's done right now is like some very intelligent people using a spreadsheet and maybe roofline analysis or maybe very, very simple simulators. And then the other part is just that because the downstream implementation takes so long, companies don't want to take big risks and make dramatic changes, like say between different generations of TPU or GPU. They want to be relatively conservative in the architectural changes so that they can be confident that they'll be able to close this design, get to a state where it's possible to manufacture it. So that, I think, to us, part of why we're so excited is we could unlock the performance gains that are possible through unusual maybe architectures if we can make the downstream optimizations fast. So the next phase would be human RTL designers will write code to implement this high level spec, which is maybe just some rows in a spreadsheet or even like a drawing of this chip. And they're also very skilled engineers, but they will potentially introduce bugs in the process of translating the spec into code, RTL code. And then that code is synthesized into a netlist, which is this graph of millions or billions of like macros, which are memory components, and standard cells, which are logic gates like NAND and NOR connected by wires. And in parallel to this, design verification is taking place. So that is to like kind of find the bugs that have been introduced into this chip to confirm basically that the high level specification is in fact faithfully implemented in the code and then later in the physical mapping of that code to silicon. And then the last phase would be physical design, which can also take like up to a year. And that's like, given this graph, let's place all of these billions of components. Let's route all of them. Let's create like, the clock tree. Let's, make sure that all physical constraints are met. So that's like the sort of the high level overview of the chip design process today.
They give me a lot of like parallels between even the programming paradigms, because when first you mentioned about like, it feels like you are doing design, like planning, and then vibe coding and creating all these designs. And then the last part is like actually making, there's a lot of nitty-gritty refinement of that. And from what you say, among this whole process, I assume like each of these cycles take like 1 to 2 years. And how much money is at stake for each design?
Oh, it's like, it costs like hundreds of millions of dollars, even billions to develop a chip, hundreds or even thousands of human experts in some cases. Like another interesting aspect is, companies will often like even do a test tape out where they will tape out a chip and they know that there will be bugs in it, and they find those bugs, and then they do another tape. They spend like 6 months, and then they do another tape out. And it's like hundreds of millions of dollars to do this second tape out. So
like each tape out hundreds of millions, and they just do.
Well, just like the time spent by these teams of like highly skilled engineers, like and then there's also of course the opportunity cost and the loss in market position of being delayed, plus the fabrication and the masks and all of that. It's just enormously expensive.
Yeah, exactly. It definitely feels like a rocket launch, like a very high stakes situation.
It's very high stakes, yeah.
Yeah, situation. And another thing that actually made me very interested, because in the beginning of the description, you mentioned about they were using spreadsheet to planning these hundreds of millions of projects. Is that real? Is that
so
what
like architecture is often done in a spreadsheet. And I think those are the decisions. These architectural decisions are where like the performance can be achieved or not. So these are very consequential.
Yeah. And then what, like among a whole processes, what do you see the most inefficient places?
So I don't know about inefficient, but places where we see opportunity to accelerate. We think physical design and design verification, because these are the two long poles. Right. Each of these can take like up to a year. They need to exhaustively search the entire spec to make sure that under no condition could this chip ever produce results that are incorrect. So exploring every possible path or to prove that that's the case is an extremely arduous, time-consuming task. And in practice, often companies, they just keep going. They keep checking and checking and checking until it's just they're out of time. And then they tape out the chip and they hope there aren't bugs, and they have these kind of post-facto fixes.
Gotcha. So the whole year, it feels to me, what I hear is like they basically run all these simulations and test out and trying to figure out all possible bugs before they actually manufacture it, because it's so expensive, I assume, to manufacture or tape out.
If they were to tape out the chip and it's incorrect, I mean, it's a complete disaster. And then I think on the physical design side, I can paint a picture about why is this process so lengthy. So first of all, there's like multiple dimensions, I guess I would say. There are billions of components. That's too much for any human to handle, and it's too much for any existing commercial tool to handle. So maybe 2 to 3 million cells max is what's possible with prior approaches. So in practice, what people do is companies divide the chip into dozens of blocks. Each block is handled by an individual or a team of individuals. And they will get in as input like this net list, and they will try to, with the help of commercial tools, get to a placement that meets all constraints and there are multiple stages of this process. So this individual maybe owns it for the global placement. They're trying to get to a global placement that works. And if it doesn't work, they will try a different solution, and then they will run this tool. They will wait many hours, potentially even days. And then they will try something else, and then it still doesn't work. And eventually they will complain. They will either try to set up a meeting with the guy who has the block adjoining to him, say, on Thursday, could we meet? And could I take more of your area? Or could you take on a timing delay for me to make it possible for me to get to a working solution? And then they have the meeting, they negotiate, they make the change. Maybe they still can't close the block. Maybe they ask someone else, or they go upstream and they say, this input is impossible for me to reach a viable solution. Can you please change the input code that was synthesized into this net list? So can you imagine, like, given there's multiple stages of this iterations back and forth between
Yeah, it's pretty complicated.
Extremely complex.
So among those like timeline of a year, it's not just like a computer is running and figuring out a bug. It's actually a huge
humans in the loop.
Human in the loop. And usually for like a common chip, we're saying, how many people are involved in this?
I mean, hundreds, even thousands in some cases.
Wow, that's a huge, basically like a huge complaint is going to be dedicated. I assume they also will be divided into departments, different teams.
Exactly. That's the other thing that's interesting here is there are opportunities for kind of co-optimization, say of RTL or of the placement or, with awareness of this physical constraints downstream. But these are actually separate teams or even departments in some cases, right? So it creates a ton of friction to kind of solve these like co-optimizations.
Exactly. Yeah. I'm curious that how your technology will help with that.
Yeah. So the way we think that chip design should be done is we think that these optimizations, like these tools that are being used, should be much faster. Like it shouldn't take many hours to get this result. Yeah. And we think that can be a game changer, and we're developing that at the company. And then the other part is we think that, agents like LLMs that can learn from experience should be assisting humans in this process and kind of orchestrating these tools and learning across them. And we think that can be a game changer and can allow us to dramatically accelerate this process.
So it's like, is it like humans actually needs to make a lot of decision process or like deliver some type of kind of code-like thing, and you are providing some tools to help them make it better? Or how does the product look like? Yeah.
So I think in the longer term, we would hope that humans can help us to provide like, what are the trade-offs here? Like, what are our objectives? Like, what is the application? Do we care about area or we care about power consumption? And to what extent? Here is a solution. Does this look good to you? More like that kind of interface, right? Higher level, like higher leverage role, like where designers can be way more productive and design many more chips, maybe more custom chips that have better performance.
It sounds a lot similar to what the software industry is moving to.
Exactly.
Like the software industry, it used to be like everyone needs to write code and then how this nitty-gritty details is. Now everyone is just sitting in front of cloud code. And is that how the future of chip design engineering will also work?
I guess we see an evolution over time.
Yeah.
So like in phase one, we want to offer more like maybe an end-to-end physical design experience where, a human expert provides information about like the trade-offs and the application or the workload. And then we, have our agents orchestrating these very fast tools, learning across and becoming much better and better over time. And then the humans evaluate the outputs. But then in the longer term, we would want the input to be more like, here is the model that we want to optimize. And then end-to-end, all the way to GDS2 clean.
So like the AI basically will be more autonomously optimizing
over time.
Over time. Yeah. Another question I wanted to step back a little bit about the three phase you mentioned about. What would be your criteria say that we're ready from phase one to phase two?
That's a really good question. And I think that's something I'm actually thinking about right now because we've made such fast progress that I think it's possible for us to move into phase two a lot faster than I had been planning originally with Azalea. And, potentially we could have phase one and phase two even overlap to some extent. Yeah. So that's actually something I'm thinking about right now.
Yeah, so I think that we had a great conversation about recursive on that. I also want to learn more about the origin of the company. 2 days after you left Google, you found this company. Tell us the story, the origin story of the company.
I guess this is something that Azalea and we had been thinking about since 2018. Like since we started AlphaChip, we thought maybe there should be a company to do this because this is just... We think, I'm biased, but I think this is very important and high impact thing to do. Like this is one of the big bottlenecks for AI. Right? AI chips are the fuel for AI. But we thought, for me, I was unlocked after I had graduated from my PhD, but that was just one of the factors. There's also like the the state of AI, of the technology, is such that we believe that now it's actually possible to achieve our long-term vision. And then the other part was the need for this has grown substantially. Like the industry needs this immediately. So we thought now is the time to strike.
That was like September to last year?
September 17th, we left Google, and we incorporated September 19th. I think we filed for incorporation on the 18th, but it takes a 24 hours to go through.
I heard that when you were planning to do this, because you and Azalea work in Google, you did very impactful work. And Jeff Dean was even trying to persuade you to stay at Google.
We really liked working with Jeff, and we had worked together with him on AlphaChip. I remember when we were leaving Google the first time and to go to Anthropic, he made a very interesting proposal, which was maybe you should have an Alphabet spin out based on, AlphaChip, and, that Google Ventures would help with that the BizOps would help us. And I thought that was like a very generous, creative, thoughtful offer. And we seriously considered it, but I think it felt like a weird middle ground where it wasn't like we weren't quite standalone and we couldn't necessarily work with the full space of possible chip partners. And maybe we would be slowed down in some way as well. So I think we thought that it was better to have this experience of working at Anthropic, it was just very obvious that that company was just going to be an absolute rocket ship just based on the strength of the team and how powerful that technology was. It was this was before ChatGPT came out and all of that. Yeah, but it was very obvious to me anyway.
The last time you mentioned you were number 20 in Anthropic.
25 right? And 26 me and Azalea, so I think I wanted to have that experience of, first of all, working hands-on on LLMs, and then also what an absolute rocket ship AI startup looks like, because I thought that this would be really valuable training data for me and Azalea if we were to ever start our own company. Yeah. And also just interesting experience.
Yes.
So I think at the time we decided not to go that route, but Yeah, and I think Jeff decided to you didn't become a spin-off of Google, but Jeff decided to invest in you. Yeah, he did. So he's still part of us in some sense. Yeah,
that's great. Yeah, that's great. And I also heard that your fundraising environment was insane. Tell us more.
I think I had obviously never fundraised before. And I'm just not expecting the experience that we had, just really intense, the level of interest.
How long was the fundraising?
Not long. I think basically the Sequoia partner had reached out to me. My advisor, when I graduated from PhD, my PhD advisor posted a photo on X of the two of us together, saying, "Oh, congrats, Anna." And then that day I got an email from this Sequoia general partner, Stephanie Jan, who actually later became our first board member. And she said, "Hey, I'm a big fan of AlphaChip. I'm also a Stanford TS alum. I'd love to get coffee and, we get to know each other."
Wow. And she also wrote a 30-page report on you and Azalea. Is that right?
Yeah. So she wrote a 30-page report about just me and Azalea, and then she wrote another long memo about the company as well.
Wow.
So I always thought, okay, Sequoia is best of best VC and so thorough, and their due diligence is so serious, but I had no idea. It was very hardcore.
How does it feel when you receive that level of due diligence?
I think they know more about me than I know about myself,
Wow.
Yeah.
There's a reason why everyone loves Sequoia.
Honestly, I find it reassuring because I know that they have 100% conviction in us, right? Because they talk to all of our prospective customers. They talk to anyone we ever worked with.
And then later, I think you finished another round just within 2 months. Is that?
Yeah, I think actually it was 1 month later, but we didn't announce it for
So what
another
made
month,
you was this like down similar time range, or was it what made you started to think about fundraising again?
I wouldn't have, but we received emails or messages from like over 100 different VCs who were, I guess, disappointed that they had missed out on this initial round. And the terms that were being offered and the partners that we could work with were just so compelling that we decided that it was in the best interest of the company to raise a Series A, but that we had not been planning to do that originally.
Yeah.
But I think it was the right call.
Yeah, it's a good call. And now you have a huge capital and in the company that you can use to achieve your vision.
Yeah, exactly. And the other part, which is interesting, is like because we had so much interest, we were able to be extremely selective about the VCs that we took funding from. And we have this very like interesting set of people who are all like, in my opinion, very impressive, like nice to work with, but also like complementary with each other and also very helpful. So I feel like it's almost like I have another team of people that I can work with or ask for help from, and who have a lot of experience in various different types of areas. And it's actually a huge advantage.
That's great. Great. Yeah. And so you have essentially built awesome teams of capital partners to help you to get a started journey. I know a lot of founders, they also are very curious about the relationship with VC partners, like especially deal with their expectations, because you had this massive and awesome like initial fundraisings also means that the company worth a lot. Do you feel pressured?
I mean, I think that it's funny because when we raised our last round, we did not show the VCs like any technical results. And then in the last few months, we made an insane amount of progress. So personally, I feel pretty good about it because I feel like from the perspective of these VCs, like we've delivered a lot in a very short amount of time. And it actually probably seems like a good thing to them that they did this. Yeah.
Yeah, that's cool. That's cool. Yeah. I think another thing that you did after you started the company, first is getting the money, but then you also build an awesome team. So tell us about the process. Yeah,
it's a good question because at least to me, like the best thing about this company is the team is extremely strong, and that's how we were able to make such fast progress. So my philosophy on hiring would be like just no compromise in terms of two dimensions. One is like we're looking for like absolutely brilliant people, and then we're also looking for people who are kind, like genuinely good to work with. And I guess my belief is that if you bring those type of people together, it scales really well. It's way more productive. And then those type of people want to work with others like that. And so it becomes like a talent magnet. So I was like, our absolute priority is to make sure that the seed of this company is like, it has this sort of kind, brilliant.
So both skills, but also the values, the culture.
Yeah, exactly. Good to work with. Someone that is a pleasure to see in the office that you would be happy to run into.
How big is your team now?
I think we're 12 people now, but we had just had another acceptance. So I guess it's going to be bigger soon. Yeah.
And is most of the team work in the office or is it hybrid? Or how does team work together?
So far we're 5 days a week in the office, which I think actually helps a lot with like moving very quickly because you have this very close like feedback loop and like communication loop. So, and I think it's, at least for now, that's the right thing for us. In terms of bootstrapping the team, I could also share a bit more. So obviously there was me and Azalia, but then we were also able to bring together kind of the core AlphaChip team. And so that kind of helped a lot. For example, like one of the people we had worked with on AlphaChip, she was a director at Cadence, which is like one of the top like chip design companies. And then we reached out to her, and she didn't tell me this at the time, but she had been writing in a notebook over and over again that I want to, work with the best AI engineers in the world, and I want to build the best AI for chip design tool in the world. And she just wrote that a number of times for 2 weeks, and then we emailed her, and we met, and then she joined us, like she accepted our offer on the spot, and then there was this. We kind of know the space of like who are the strongest people in this area. So we emailed this person. he's like absolutely amazing. Like, do you know DAC? It's like the NeurIPS of chip design. So he won Best Paper Award at DAC, first author, twice. And then he just actually, like last month, he won another ASP DAC Best Paper Award. He's like, he was a professional Go player as a child, just amazing. So we emailed him, like cold email, we'd never met before. He immediately responded. 2 weeks later, he accepted our offer on the spot. But I remember telling him, like, we're getting the core AlphaChip team together. And he's like, you guys are the best of the best. Like, I want to be part of that. Right. So that's kind of the seed. And then we bootstrap from there.
Yeah, you did an amazing job. Like the talent density is so high. And we all heard about a lot of stories in the Silicon Valley about talent war. And look, Zuckerberg used 100 million to recruit AI scientists. And I wonder, what is your recipe to recruit such talented?
Oh yeah, we have candidates who have those like $20 million per year kind of offers. I think at the end of the day, it's about meaning. Like, what is something meaningful to work on? Like, what would be fun? Like, I want to work with people who are smart and kind and do something that I think matters. I mean, and the other part is this, like, our company has the potential to be, like, if we succeed in our mission, we would be a multi-trillion-dollar company.
After you have the capital, you have the greatest team. Also, it's about working with the best customers.
Exactly,
And how do you find customers?
Actually, they find us, which is...
Wow.
So something like almost every major semiconductor company in the world has reached out to us and expressed interest in working together. So we actually don't have enough capacity to work with all of them immediately. So we have to pick. And, you know, we consider a number of different things in our partners. Like, one would just be like, are they a good partner? Will they be collaborative? You know, would they share with us, you know, what they need and what they want? Be open, right? So that's one aspect. One would be, you know, there's sort of strength in the semiconductor market, how much we can learn from them in that sense too.
The chip has become like bottleneck of the whole industry. As we are doing the scaling law, we need more and more computations. But right now there's a shortage in terms of chip, there's memory chips, there's core chips, they're all in shortage. The question I have is that given there's such a demand in the industry, are you worried there will be more competitors coming into the spaces and working?
I remember, so this person that I was just talking about earlier, from NVIDIA, he's like also extremely kind, sweet person. And I remember someone asked us that question, another customer. So are you worried about competitors in this space? And then he said something like, competition is good because then you can show that you're the best. But in this very sweet way, I guess I agree with that, right? I think we're not afraid of competition. I think competition is good. I think this industry, chip design, needs more competition. We need to make progress. This is a bottleneck for AI and for progress here. So we're not worried about it. We like that.
We're talking about the industry, which is moving very, very fast. One fundamental thing that is driving the industry is the scaling law.
Yes.
Like, what is your view of scaling law?
So in some sense, you know, it's kind of like the bitter lesson, right? Yeah. In some sense, all that matters is compute. And I think that scaling laws show that in a very clean and beautiful way. So I guess I can describe what those are. These were developed by physicists who came into AI. So maybe that's part of how they have this mathematical beauty. But there's this idea that as you apply more compute at pre-training, or actually there's scaling laws related to test time or inference as well. As you apply more compute, you just get better performance in a very clean and deterministic way across many orders of magnitude of compute. So therefore, like, if you can design chips that are better suited to the workloads, to the ML models, you can effectively bend the scaling laws. You can get effectively more compute applied to this problem and more intelligence. You
mentioned about the great concept of bend the scaling law. And what do you think are some conditions that are needed for the scaling law to be bended?
I mean, so you can change algorithms, right, to change the exponent in this power law relationship. But the other thing you could do is you can make better computer architectures that, you know, effectively give you a compute multiplier and push you further out in the scaling law.
There's these two factors that determine the scaling law. One is the algorithms. One is actually the computation or the computation architecture on that. So,
and then there's the fit. And in some senses, it's always like a full stack.
Yeah.
So it's never the chip in isolation. It's never the algorithm or the model in isolation. It's also like how you map the algorithm onto this chip. Yeah. How you do the compiler passes, all of that. So it's all holistic. But
it's co-design thing.
Yeah, co-design.
And because I know that in the industry, a common paradigm people have been doing that, they'll buy off-the-shelf like chips from NVIDIA or other vendors, and they will design and just work on this algorithm, as if algorithm and hardware are completely isolated thing. Do you agree with that?
No, I mean, maybe for prototyping, that's fine. But if you want to, like, given that people are spending hundreds of billions of dollars on AI inference and it's just only growing. Like once you have some model that you're deploying to like millions, hundreds of millions of users, like you absolutely should care about co-optimizing.
Yeah. I think you mentioned about one point, which is that the cost is also very important, especially if you are in just doing research, maybe that's fine. It's small scale. But if you have a popular app like ChatGPT or Cloud, you serve hundreds of millions of users, the cost is very, very important for that. And I assume that that's also the reason why a lot of chips need to be redesigned, or is that?
I mean, that's our philosophy here, is we think that, there's a cost of these models, which is, one question about like profitability of AI as an industry overall. You want to make sure that margin is positive.
Right.
And then there's also like the carbon footprint of these models. So there's that part too. So like there's many reasons that you should care about the efficiency. And we think maybe the solution, especially as this AI technology becomes more and more prevalent in every aspect of our lives, and there's all sorts of, there's these models like ChatGPT, but maybe there's also like robotics and embedded devices, AR, VR, sensors, space exploration, all sorts of other types of application that could benefit from custom chips. Maybe applications that aren't possible without custom chips. Like maybe you have some like, drone that assists you with something, but it needs to be extremely power efficient to be intelligent enough to do whatever the application is. And maybe that's not possible with just existing garage parts applied to the problem.
Exactly, yeah. And I know that because you are helping the chip design that empower a lot of the LLM applications, the type of application that actually will have impact to you as well. So the LLM models evolving rapidly, and there has always been people saying, okay, this is the architecture of LLM has been stable, right? But it turns out that there's always some improvement that's happening. The question I have is that the rapid involvement of the LLM applications, does that have impact to you as you are building the chip design?
Yeah, I mean, actually, that's part of our motivation. LLMs evolve so rapidly, and yet chips are so slow to evolve. Like, if you think about it, like, if you're a chip maker and you're designing a new chip, you have to consider, okay, like, in 3 to 5 years, what models, like, will be prevalent? And actually, that's pretty much impossible, right?
Impossible. I couldn't imagine, like, 6 months.
And so that's why you have to develop these very relatively general purpose chips.
Yeah.
And then, I don't know if you've heard the maxim, like, good for everything, good for nothing. That's right?
Yes.
It's like, so you there's always this trade-off. That's why, like, we think it would be so valuable to be able to shorten this design cycle, because then you could afford to design more custom chips that would then accelerate or provide, like, orders of magnitude better performance.
I see. So that's actually because you mentioned about in the phase 1, you want to reduce the length, the cycles.
Exactly.
So actually that is the recursive part. It actually helps to accelerate LLM development as well.
Exactly. And both edges, right? So the other part is that LLM, like AI researchers, are thinking, okay, I'm designing this model. These are the chips that exist right now. It's a hardware lottery. Right. Only ideas that work on current hardware are viable, really.
Right.
Be given the bitter lesson or the scaling loss.
Yeah.
So there's this deadlock in both directions.
That's actually a great question, because a lot of LLM researchers, when they do research, and because the space of LLM research is much faster than the chip design, they will basically assume the chip will never change.
Exactly.
And they will explore the architecture on top of that. They basically like, let's fit in GPU, which is designed for gaming, and they say what architecture fits for that. What do you think about the futures when you made the whole feedback loops for the chip design to be like, or maybe every few weeks you get a new chips on that? How does it impact LLM research?
I mean, I guess the way I think about it is in phase 3, we could achieve true coevolution of AI and the hardware that fuels it or its physical substrate. And what I think is that maybe right now we're in this kind of local optimum in terms of both the chip and the model. And there may be some place out here, some global optimum that looks wildly different in terms of the computer architecture and also in terms of the neural architecture that would be like way, way more efficient. And I want to get there.
Yeah. That's a beautiful vision. Like you put a great way, is that there's a local optimum, that deadlock situation that happens. Like the LM researcher assume hardware never change, so they design architecture. And then after they design architecture, the chip designer has to assume that architecture is the same. So it's kind of a deadlock situation.
Exactly.
Yeah. I'm very curious about your visions in the future about this co-design thing, which is that when the LM researchers design kind of the algorithms, it also would consider about hardware. And do you have any ideas how that would look like?
I mean, in the final stage of the company, these LLM researchers would be at our company working together with the chip designers, or I guess maybe the algorithms. So that would be a totally different model. I think in the shorter term, I think there's this whole space of different levels of like a spectrum of different levels of customization. Like you could go, okay, CPUs, GPUs, you could go to specific to the architecture. You could go specific to the weights. You could go specific to the expected distribution of the input data that is likely to be coming in. I think that all of these, you kind of shift what's a viable like path. And I think that's interesting and exciting. One thing that would be cool, I think, would be if the LLM researchers could come up with an architecture, and then while they were training the model, the chip could be designed and then fabricated, because it takes 3 to 6 months to train a frontier model. What if you could have a chip in that time? That would be cool. But that, of course, would constrain it that it was just custom to the architecture, but not the weights. But anyway, these are all interesting questions to me.
That's actually such a fascinating future in which that we basically can design and the algorithm, and then we'll make the chip on the fly for that algorithm. And it reminds me a quote from Steve Jobs, like anyone who like to build great software needs to build the hardware. So it sounds very similar to that. I also see that recently there have been companies who's trying to kind of making the model ways to be kind of hardwired, rather than being an abstraction on top of the GPU. Do you think that is a trend? Or
I think it's very interesting. As I was suggesting, I think that creating very fast chip design tools enables all of these types of bets along the whole spectrum of specialization, including burning in the weights, which I think is personally very interesting. Yeah. And I think in terms of your point about the hardware, software, like MIT actually, course 6 is EE and CS. And I think MIT didn't believe that you could have them be two separate departments, because when you're writing code, you should always be thinking about the hardware and vice versa.
Related to that, what are the other interesting technology trends that you're observing in the space you're?
I think so. Something else that I think is interesting is, say, kernel bench. So
kernel bench.
like using AI to design kernels is this emerging area. Actually, my co-founder Azalia's lab, they released this benchmark called Kernel Bench that's become quite popular. And one of the interesting things is how quickly it's becoming saturated by AI techniques. So, as AI models become increasingly effective at designing kernels, it opens up new questions about maybe we could worry less about the compiler. So one of the questions that you can have about like designing new chips would be, well, how can you quickly provide the software layer to make them programmable? And so, one answer could be that if these chips are ultra custom to just one particular model, then maybe they don't need to truly be programmable. But then the other possible answer could be, as AI becomes more able to design kernels, maybe we can remove some of these intermediate levels of abstraction and have AI models like write assembly basically, and maybe even get better performance. So that's also very interesting, and I find that kind of inspiring, and it makes me optimistic about the future of this direction.
Yeah, that's actually a super interesting trend that you mentioned about. Like the AI is better and better at the lower level programming, like kernel. Like
yeah, exactly.
A lot of the common conception people have is AI is very good at writing JavaScript, or it's very high level. But it turns out it's just a very powerful technology understand any type of programming on that. And there is the whole trend of like rebuild the whole computer from scratch that is designed for AI. And you mentioned about this AI for building kernel. I'm curious, like as AI started to do more and more low level design, like design kernels, design chips, what is the difference between the AI writing JavaScript or Python script, and the top level?
There's like the AI designing kernels like models, and I think those are actually just LLMs that are post-trained to do this. And then there's like questions of like what type of AI methods should be used for tasks like physical design, where you're placing millions or billions of components and routing them. I think you could potentially use an LLM to do that directly. I don't think that would be the most effective like technique to use. That's not what we're doing in our company.
Most of people, when they hear about AI, they will think large language models or predict next word. And in fact, that's just a subset of the whole AI field.
Exactly.
And there's a lot more other fields. You briefly mentioned about that you are actually not, LLM is not the only technology used in your company.
It's just part of the solution.
Part of technology. So what are the technology trends that you are betting on with to achieve the vision of the three phases you have?
So I would say large language models absolutely are extremely powerful. We are using them at our company. We're even pre-training. So we're pre-training, we're post-training, we're RL post-training, we're doing test time scaling. We absolutely believe in that. We're also using reinforcement learning methods to learn from like fast feedback signals. Yeah, exactly. And then, we're also using other types of AI methods or deep learning based methods that are extremely fast, that are more suited to, say, maybe graph-shaped problems. Like, for example, in AlphaChip, we weren't using like an LLM architecture. We're using like a graph-based neural net.
Yeah. And I think that's actually bring up a very interesting topic is about at which scenario LLM would be a good model and which scenario LLM is not good and we should use more specialized AI for that. What is your take on this?
Of course, it's like a very deep question, but as a heuristic, what I would say is LLMs are good at the types of tasks that humans are good at. So if it looks like a language base, if it looks like writing code, if you want to be able to like learn, that I think LLMs are, and you want to be able to understand human intent. That's another reason you should use LLMs. But if the problem looks like something that humans aren't particularly good at, like placing billions of components individually, while maintaining like 8 different or 9 different physical constraints, then I would say LLMs are probably not the right fit.
Yeah, you actually bring such a powerful mental framework for people to understand LLM. And like LLM is basically a recreation of humans. So if a human are good at solving a problem, LLM can solve it faster and a larger scale. But if human cannot solve a problem, then LLM usually cannot.
Exactly. I mean, it's like, of course, a fuzzy heuristic. And, humans did do some of these types of tasks in the past, but it was not a very good fit for them, right? Mm-hmm. So that, yeah.
I think that is also very related to the work you do in AlphaChip and also a lot of reinforcement learning work. For example, even in the AlphaGo, there was 2 stages. The first was learning from human experiences. But then later they switched to AlphaZero, which is like completely solving from problems from scratch. And it can give solution that no human can even imagine from that. And I wonder from your perspective, for example, in the chip design process, what are the kind of the examples of things you feel humans are very good at? We should use LLM, and other parts like there's no way human can do that. Then we should build a specialized model for that.
So in chip design, I think that maybe RTL generation and to some extent design verification.
The RTL is for?
It's basically like a task that humans currently do, but sometimes lossily. It's code. It's code generation task.
Code generation, yeah.
So I think because it's like a language problem, I think LLMs are a good fit. But I think that paired with, exhaustive verification methods. Because that's a weakness of LLMs. You have to verify. And the weakness of humans.
Yes, you actually mentioned a great point. Now, actually, the whole thing become recursive. The beginning part, you mentioned about you were focusing on design verification, which is actually the verification is like a testing, a QA of the same. And we humans are very good at writing things, but it's very hard to exhaustively testing and verifying all the things. And I'm curious that because this part you mentioned about having LLM by itself, it started from a hallucination problem, and we're trying to make LLM more reliable in all areas. And in your cases, you are solving design verification problems. What are mechanisms you are using to make your AIs more stable and reliable than the off-the-shelf models we see?
I mean, I think at the end of the day, just you have to verify that's the case for humans or for AI outputs. Just do design verification exhaustively. And then my belief about like what would be effective here is that you use some kind of formal tools and then you use LLMs to explore the space of what would be the most efficient way to prove correctness.
Yeah, and exploration is also what humans are very good at.
Yeah, exactly.
Yeah. And so it's like kind of there's a framework, and the framework can be created by other types of mechanism, not necessarily LLM. I think a lot of people now put in the harness, something like that, and they have LLM to just like follow the rules or do the exploration, but within that harness or within that guardrails they create.
Yeah, I mean, I guess what I would say is like have the LLM like on the RTL generation side, have the LLM generate the code. And what I think is exciting is then use these very fast feedback loops to, inform the generation of that RTL. But then at the end of the day, verify everything. Like, and that's necessary, whether that's from a human or from an AI. Trust,
but verify.
If you don't trust.
AI we probably shouldn't. Yeah, cool. So it's fantastic to chat with you about the vision I had about the chip design. And I also want to take a step back for you. Now you have went through the journey of being a researcher, and now you are a founder. Among the experience you have, what is the biggest takeaway you got so far?
I think that like when I was, leaving to start this company, people asked me like, well, why would you leave Google? And I remember saying like, oh, I can work with more different chip makers and see like a larger space of designs. And also I think we can move faster as a standalone company. I thought that was true when I said it, but it was like 10 or 100x more true than I thought. Like every day at this company feels like a month in a very fun and exhilarating way. So I'm just so glad that we did this. And I also feel like kind of unleashed or unlocked. Like, you know, when you're at a larger company, you have to convince so many layers of people. Like it kind of feels like you're playing a game of chess, but you can't move the pieces. You have to convince 10 different people who are holding the piece to make the move that will make all of you win. But then, you know, these other people you're talking to, they have their own heuristics like, oh, I should never take another piece because often that means that my piece gets taken back or something like that. So it's actually, Murray, my husband was saying like, you just seem so much less stressed out now that you're a founder or CEO of a company, which is, I think, a surprising thing, but it's true. It just feels incredible to just be able to execute and do what makes sense and have such a strong team and move fast.
A lot of people, they say founders' life are very stressful. I think founders' life definitely are busy. I can say you're super busy. But I think the stress, being whether stressful or not, is an independent question whether you're busy or not. Is whether you can get your energy to the right thing. And
exactly.
If you work in a big company, a lot of times where you have energy but you couldn't get things done, that also causes stress.
Actually, more stressful.
More stressful. Yeah, a lot of people don't pay attention. They will over anchor on the stress of founders, but the stress of not being able to do things is also very big. The next question I have is that I think your experience will inspire many researchers who started to pursue their own dreams and started doing own startup. And I want to learn from you, is like, what would be the one advice you have to them that they should pay attention to if they want to go through the same journey?
I guess for me, I always, I was thinking about doing a company for a long time. And I had the right partner, like Azalia, someone I worked with like closely for 10 years. And we went through like crazy things together. We worked at like, Google Brain, Anthropic, DeepMind. We even worked in parallel at Stanford. So I had that, which I think is a requirement. But I also felt that I only wanted to start a company if I felt like this company needs to exist and it needs to be me that does it. And so I feel like all of the conditions were met, and then I did it, and it's gone well so far. So I guess that my advice would be to make sure all of those conditions are met, and then I think you'll be successful.
Mm-hmm. Yeah. So it's like keep the dream, but also like understand whether it needs to be done. Like it needs to be you to do this.
If you're like, oh, this is kind of a good idea, maybe it makes some money or something, and then I don't know, maybe don't bother. Or if you're like, oh, like maybe this is something that needs to happen, but actually anyone could do it. Maybe go do the thing that it needs you.
Yeah, exactly. That's actually related to a lot of founders when I talk about founder market fit. Why you should work on this. So I think what I hear you say is that figure out the founder market fit.
What is the company that you have to build?
Exactly. Yeah. Awesome. Really great to have this conversation with you. And every time we chat, I feel like there's so much fun. And we'd love to have you come back for the episode 3.
Sounds great.
Yeah.
It was a pleasure.
Thanks for watching the full interview. Don't forget to subscribe to our YouTube channel and turn on notifications so you never miss the next one.